Tonight, we are going to walk slowly to the very last moment of the cosmic stelliferous epoch and stand beside the final star that will ever burn in this universe. The star is out there, not in any specific direction we can point to from our current perspective, because the star has not yet formed. But the physics that will eventually produce it is in the cosmos now, embedded in the various stellar populations and gas clouds and gravitational dynamics that will, across enormously long stretches of cosmic time, eventually conspire to produce one specific final stellar object. That object, when it finally exhausts its nuclear fuel and stops shining, will mark the absolute end of the active stellar epoch in the universe. Tonight, we're going to walk through what the final star will look like. The work has been done in considerable detail by theoretical cosmologists working on the deep cosmic future. The predictions are not certain in their finest details, but they are reliable in their broad outline. No one predicts the final star's specific behavior in detail, but the broad framework is reliable. The final star will be smaller than any star you have ever heard about, dimmer than any star you have ever read about, and longer-lived than any star you have ever imagined. The cosmic stelliferous epoch, the era in which stars exist, began approximately 100 million years after the Big Bang. We are currently approximately 13.8 billion years into that era. The era will continue by every available calculation for approximately 10 to the 14th years from the present, which is approximately 10,000 times the current cosmic age. By that future time, all the stars that formed through the normal stellar formation channels will have died, but the era will not actually end at 10 to the 14th years. The very last stars will not be the products of the original stellar formation channels. They will be the products of rare events occurring during the early degenerate era, in which brown dwarfs collide and produce merger objects with masses just above the threshold for hydrogen fusion. These merger-produced stars will burn for trillions of years each, with the very last of them lasting until approximately 10 to the 17th years from the present, possibly longer, depending on the specific assumptions about brown dwarf collision rates and merger product properties. By the end of tonight, you're going to understand that the final star is, in this sense, the boundary marker between the active stelliferous epoch and the long, quiet era that follows. After the final star exhausts its nuclear fuel and stops shining, no other star will ever ignite anywhere in the cosmos. The universe will, from that moment onward, be entirely dark in the sense that no active hydrogen fusion will be producing fresh starlight anywhere. The cosmos will continue to exist for enormously longer than the stelliferous era ever lasted, but it will continue without any active stars producing visible light. Tonight, we're going to walk through 5 specific truths about the final star. Each one is a real prediction based on well-understood physics. Each one has implications for the broader picture of cosmic evolution. Each one helps explain what the absolute end of the active stellar epoch will actually look like in concrete physical terms. Before we get started, sit with what is at stake here. The cosmos has produced approximately 200 billion galaxies, with each galaxy containing approximately 100 billion stars on average. The total number of stars that have ever existed in the cosmos, integrated across the entire stelliferous era, is approximately 10 to the 23rd power. The final star we are walking toward tonight is one specific stellar object among that enormous population, the very last one to ever burn through the standard nuclear processes. It is, in this sense, both a specific physical object and a category boundary for the entire cosmic stellar inventory. The 5 truths are these. The first truth is that the final star will be smaller and dimmer than essentially any star that has ever been observed by human astronomy. The mass will be at the absolute lower limit for sustained hydrogen fusion, approximately 8 to 9% of the mass of the Sun, possibly slightly higher. The surface temperature will be only 2,000 to 3,000 Kelvin, far cooler than the Sun's 6,000 Kelvin surface. The luminosity will be approximately 1/10,000th of solar luminosity, far below the brightness of any star currently visible to the naked eye from Earth. The second truth is that the final star will burn for an extraordinarily long time, far longer than any star you have ever heard about. The very smallest hydrogen-burning stars in the modern cosmos, with masses approximately 1/10 of solar, have main sequence lifetimes of approximately 10 trillion years, which is 1,000 times the current age of the universe. The final star, which will form much later in cosmic history through a brown dwarf merger event, will burn for an additional period that depends on its specific mass and metallicity, but that may exceed 10 trillion years from its formation. The total cosmic time during which any single star can persist is, in this sense, much longer than the current cosmic age. The third truth is that the final star will die in essentially perfect silence. Unlike massive stars that end their lives in dramatic supernova explosions, small stars do not produce supernovae. The final star will simply exhaust its hydrogen fuel, cool gradually, and eventually transition into a small, dim white dwarf. The transition will happen over hundreds of millions of years, with no dramatic event marking the moment when the active stellar burning ends. The death of the final star will be, in this sense, one of the quietest events in cosmic history. The fourth truth is that the final star will mark the absolute boundary of the cosmic stelliferous epoch. After the final star dies, no other star will ever ignite anywhere in the cosmos. The brown dwarf collisions that produce merger-driven stars will continue at progressively lower rates, but the rates will eventually decline to essentially zero as the available brown dwarf population is depleted. The very last merger-produced star will exhaust its fuel, and, from that moment forward, no active hydrogen fusion will be producing fresh starlight anywhere in the universe. The fifth truth is that the cosmos will continue after the final star dies for enormously longer than the entire stelliferous epoch ever lasted. The degenerate era will continue until approximately 10 to the 39th years. The black hole era will continue until approximately 10 to the 100th years. The dark era has no defined end. The ratio between the cosmic future after the final star and the cosmic past during the stelliferous era is approximately 10 to the 85th power, or more. We are alive in this sense during a brief early phase of cosmic history, with the vast majority of cosmic time being characterized by configurations without active stars. 5 truths, 5 facets of the absolute end of cosmic stellar activity. By the end of tonight, you will have walked slowly through each one, with enough detail to feel the weight of the final cosmic moment and enough perspective to see why the death of the final star marks one of the most important transitions in the entire cosmic story. Pattern interrupt. The tone of tonight should not be despair. The cosmos after the final star dies is not a sad cosmos. It is simply a different cosmos, with different processes operating and different physical features being dominant. The stelliferous era is one chapter in a much longer cosmic story. The chapter eventually ends, but the story continues. Whatever observers might exist after the final star dies, if any do, will see a cosmos that operates by different physical principles than the active stellar cosmos we currently observe. Now, let's begin with the first truth. The specific properties of the final star, considered as a physical object that will form approximately 10 to the 17th years from the present. The final star will be, by every available calculation, at the absolute lower mass limit for sustained hydrogen fusion. The minimum mass for hydrogen fusion in a stellar core is approximately 0.075 to 0.08 solar masses, depending on the specific composition of the star. Objects below this threshold can briefly produce some nuclear fusion reactions during their gravitational contraction, but they cannot sustain fusion long enough to qualify as proper stars. They become brown dwarfs, gradually cooling without ever achieving the steady main sequence burning that defines stellar life. The final star will form through a brown dwarf collision event during the early degenerate era. The collision will combine two brown dwarfs, each with masses below the fusion threshold, into a single object whose total mass exceeds the threshold. The merger product will, if the collision dynamics are right, ignite hydrogen fusion in its core and begin to burn as a small but proper star. The mass of the final star will likely be close to the minimum fusion threshold. The collision dynamics will tend to produce merger products with masses near the sum of the two original brown dwarf masses, with some material being lost through the violent dynamics of the collision. The resulting merger product mass distribution will, by various theoretical estimates, be biased toward the low end of the stellar mass range, with most merger products having masses between 0.08 and 0.15 solar masses. By the end of tonight, you're going to understand why this matters for the brightness of the final star. The luminosity of a hydrogen-burning star depends very sensitively on its mass, with low-mass stars being much less luminous per unit mass than higher-mass stars. The relationship is approximately a power law, with the luminosity scaling as the mass raised to the power 3 to 4. A star with mass of 0.1 solar masses produces approximately 1/1000th of the solar luminosity. A star with mass at the absolute fusion threshold of 0.075 solar masses produces approximately 1/10,000th of the solar luminosity, possibly less. Pattern interrupt. To put these luminosities into context, the Sun produces approximately 4 times 10 to the 33rd ergs per second, or about 3.8 times 10 to the 26th watts. A star of 0.1 solar masses produces approximately 4 times 10 to the 23rd watts. A star at the minimum fusion threshold produces approximately 4 times 10 to the 22nd watts, which is far below the energy output of any familiar reference. The total luminosity of the final star is comparable to the heat output of a small ordinary star in the modern Milky Way, but spread across an entire stellar surface rather than concentrated in any specific location. The surface temperature of the final star will be similarly modest. Low-mass stars have low surface temperatures because the relationship between mass, luminosity, and surface area produces a specific relationship between surface temperature and stellar mass. A star with mass approximately 0.1 solar masses has a surface temperature of approximately 2500 Kelvin. A star at the minimum fusion threshold has a surface temperature of approximately 2000 Kelvin or slightly lower. The temperatures are much cooler than the Sun's 6000 Kelvin, with implications for the spectrum of the emitted radiation. The radiation from the final star will be primarily in the infrared, with relatively little visible light being emitted. The peak of the thermal spectrum at 2000 Kelvin is at approximately 1400 nanometers, which is in the infrared band, rather than the visible. Some visible light will be emitted at the higher frequency end of the thermal spectrum, but the visible band, luminosity, will be much smaller than the total bolometric luminosity. To any observer with eyes similar to ours, the final star would appear as a dim red point of light, barely above the threshold of detection. By the end of tonight, you're going to understand that the final star, considered as a visible object, will be dimmer than essentially any star that exists in the modern universe. The dimmest stars currently visible to the naked eye from Earth are approximately 6 magnitudes brighter than the threshold of human vision, which corresponds to luminosities approximately 1/10,000th of solar. The final star, with luminosity at or below this level, even before accounting for distance effects, would be on the boundary of detectability for any human-like observer. Tonight, we're going to walk through the specific physics of M-dwarf evolution, because M-dwarfs are the longest-lived stars currently observed in the modern cosmos, and their properties provide the empirical foundation for understanding what the final star will actually be like. M-dwarfs, also called red dwarfs, are the lowest mass stars in the standard stellar classification scheme. They have masses ranging from approximately 0.08 to approximately 0.6 solar masses, with the lower bound being the minimum mass for sustained hydrogen fusion. The smallest M-dwarfs are at the absolute lower limit of what counts as a star, with masses only slightly above the brown dwarf threshold. The empirical study of M-dwarfs has been substantial over the past several decades. The objects are extraordinarily common, with approximately 75% of all stars in the Milky Way being M-dwarfs. The proximity of many M-dwarfs to Earth allows detailed study of their properties. Recent exoplanet surveys, including the TESS mission and various ground-based programs, have specifically targeted M-dwarfs because their small sizes and low luminosities make planetary transits relatively easy to detect. By the end of tonight, you're going to understand that the M-dwarfs in the modern Milky Way have ages ranging from very young, just-formed objects to objects approximately as old as the universe itself. The oldest M-dwarfs are essentially primordial, having formed early in cosmic history and continuing to burn through their hydrogen at their characteristic slow rates. Because the M-dwarf main sequence lifetime exceeds the current cosmic age by factors of approximately 100 to 1000, no M-dwarf has yet had time to complete its main sequence evolution and exhaust its fuel. Pattern interrupt. The implication is striking. The cosmos has not yet had time to produce a single M-dwarf white dwarf through standard stellar evolution. Every white dwarf currently observed in the cosmos comes from a more massive stellar progenitor that completed its evolution within the available cosmic time. The white dwarfs from M-dwarf progenitors will only begin appearing approximately 10 to the 13th years from the present, when the very oldest M-dwarfs finally complete their main sequence evolution. The specific lifetimes of M-dwarfs have been calculated by various theoretical groups. The leading calculations by Gregory Laughlin, Peter Bodenheimer, and Fred Adams at the University of California, Santa Cruz and the University of Michigan were published in 1997, the same year as the original Adams and Laughlin Deep Cosmic Future Framework. The calculations established the specific main sequence lifetimes for M-dwarfs across the full mass range, with the results being one of the foundations of the deep cosmic future cosmology. Now, let's begin. The lifetime for an M-dwarf of 0.1 solar masses is approximately 10 trillion years. The lifetime increases as the mass decreases, with the relationship being approximately a power law. A star of 0.08 solar masses has a lifetime of approximately 12 trillion years. The smallest possible stars at the absolute minimum mass for hydrogen fusion have lifetimes possibly exceeding 10 trillion years, depending on the specific assumptions about the late-stage stellar evolution. By the end of tonight, you're going to understand that the long M-dwarf lifetimes are a consequence of the specific physics of low-mass stellar evolution. The convection that we discussed in earlier truths plays a crucial role. Full convection, present in stars below approximately 0.35 solar masses, means that the entire hydrogen supply is available for nuclear burning, rather than just the hydrogen in a small central region. The convective mixing extends the lifetime by factors of approximately 10 compared to what would be expected for non-convective stars of the same mass. The slow burning rate in low-mass stars is another contributor to their long lifetimes. The rate of nuclear fusion depends sensitively on the central temperature, with cooler cores producing slower fusion rates. M-dwarfs have central temperatures only slightly above the threshold for proton-proton fusion, which means the burning rate is much slower than in higher mass stars with hotter cores. The slow burning rate stretches the lifetime even further. Walk with me through one specific empirical implication. The oldest M-dwarfs in the modern Milky Way are approximately 13 billion years old, having formed during the cosmic dawn era or shortly thereafter. Their measured properties, including their surface temperatures, luminosities, and abundance patterns, are consistent with the theoretical predictions for stars of their masses and metallicities at their specific ages. The empirical agreement provides confidence in the theoretical framework that predicts the much longer lifetimes for M-dwarfs of the various masses. The brown dwarf merger stars that we have been discussing as the candidates for the final star are essentially M-dwarfs in their properties. The merger products that ignite hydrogen fusion will have masses near the minimum threshold for fusion. They will be small, dim, fully convective, and slowly burning. Their properties will be similar to the smallest M-dwarfs currently observed in the modern cosmos, with the main difference being the mechanism of formation rather than the resulting stellar properties. No one expects, on first thinking about stellar evolution, that the longest-lived stars in the cosmos would have lifetimes 1,000 times the current cosmic age. No one predicts that the empirical observations of M-dwarfs in the modern cosmos would provide such direct input to the question of what the final star will be like. Absolutely no one anticipates the way the specific physics of low-mass stellar evolution combines to produce the enormously long lifetimes that characterize the longest-lived cosmic objects. No one predicts the specific implications, but they unfold from the basic physics. The final star are direct. The final star will be similar in its properties to the smallest M-dwarfs currently observed in the modern cosmos. The empirical study of these objects provides direct input to the theoretical predictions for the final star's properties. The final star is, in this sense, not a fully speculative object. It is a categorical endpoint whose properties can be predicted from the well-understood physics of stars whose smaller cousins we currently observe. Hold this image. M-dwarfs are the longest-lived stars currently observed in the cosmos. Their lifetimes exceed the current cosmic age by factors of approximately 100 to 1000. Their properties have been studied empirically through extensive observations of the nearby stellar population. The smallest M-dwarfs provide the empirical foundation for understanding what the final star will be like, with the final star being a similar object, but produced through brown dwarf merger rather than through standard stellar formation. The work of understanding the final star is, in this sense, grounded in empirical study of the M-dwarfs we can directly observe today. Hold this image. The final star is small, dim, and cool. Its mass is at the absolute minimum for sustained hydrogen fusion. Its surface temperature is barely above the temperatures at which proper stellar fusion can be sustained. Its luminosity is at the lower limit of what any star can produce while still being properly called a star. It is, by every available measurement, a minimal star, the smallest possible stellar object that the laws of physics allow to exist as a sustained nuclear fusion source. The second truth is that the final star will burn for a length of time that no human framework can really hold. Tonight, we're going to walk into this carefully because the lifetime of the final star is one of the most striking features of the deep cosmic future, and the specific timescale is worth understanding in some detail. The basic physics is this: the lifetime of a hydrogen-burning star depends on two factors. The first factor is the total nuclear fuel available, which is essentially the total mass of hydrogen in the star. The second factor is the rate at which the fuel is consumed, which depends on the conditions in the stellar core. The lifetime is the ratio of these two quantities, with longer-lived stars having more fuel per unit consumption rate. For high-mass stars, the consumption rate is enormous and the lifetime is short. A star of 20 solar masses lives for approximately 10 million years, burning through its hydrogen so rapidly that the available cosmic time is far longer than the stellar lifetime. For solar mass stars, the consumption rate is moderate and the lifetime is approximately 10 billion years, comparable to the current age of the universe. For low-mass stars, the consumption rate is very slow and the lifetime is enormously long. By the end of tonight, you're going to understand the specific calculations for very low-mass stars. The lifetime scales approximately as the inverse cube of the mass, with some additional corrections for the specific stellar physics. A star of 0.1 solar masses has a lifetime of approximately 10 trillion years, which is 1,000 times the current age of the universe. A star at the minimum fusion threshold, with mass approximately 0.075 solar masses, has a lifetime of approximately 10 to the 13th years or longer, depending on the specific assumptions about the late-stage evolution. Pattern interrupt. The final star, which we have established will be at or near the minimum fusion threshold, will have a lifetime in the range of 10 trillion to 100 trillion years from its formation. Combined with the cosmic time required for the brown dwarf collision event that produces it, the moment when the final star finally exhausts its fuel will be approximately 10 to the 17th years from the present, possibly slightly later. The specific value depends on the details of the brown dwarf collision rate and the specific properties of the merger product, but the general range is consistent across the various theoretical estimates. To put this lifetime into context, it is useful to compare it to other cosmic timescales. The current age of the universe is approximately 10 to the 10th years, or 13.8 billion years. The lifetime of the final star will be approximately 1 million to 10 million times the current age of the universe. The final star, in this sense, will live for far longer than the entire current cosmic history, multiplied by a substantial factor. By the end of tonight, you're going to understand why this is, despite the long duration, still a finite stellar lifetime. The final star is not eternal. It will exhaust its hydrogen fuel through the same nuclear processes that produce energy in all hydrogen-burning stars. The processes are slow for low-mass stars, but they are not zero. Eventually, even a star at the absolute minimum fusion threshold will use up the hydrogen in its convective core and reach a state where sustained fusion is no longer possible. The convective structure of low-mass stars is one of the more important features for understanding their lifetimes. Stars with masses below approximately 0.35 solar masses are fully convective throughout their interiors, with the hot gas circulating from the core to the surface and back through large-scale convective motions. The full convection has the effect of allowing the star to use essentially all of its hydrogen as fuel rather than just the hydrogen in a small central region. The convective mixing extends the lifetime substantially compared to what would be expected for a star that could only burn the hydrogen in its immediate core. Walk with me through what this implies for the final star specifically. The final star, with mass approximately 0.075 to 0.1 solar masses, will be fully convective. Its entire hydrogen supply will be available for nuclear burning, with the convective mixing continuously bringing fresh hydrogen to the core for fusion. The star will continue to burn at a slow, steady rate for the entire duration of its main sequence lifetime, with very little variation in the burning rate over time. The metallicity of the final star will also affect its lifetime in specific ways. The final star will form during the early degenerate era, by which time the cosmic chemical inventory will be substantially enriched by previous generations of stars. The brown dwarfs that merge to form the final star will themselves have inherited the enriched chemical composition. The final star will therefore have a metallicity comparable to that of modern stars, with various heavy elements being present in its composition at solar or somewhat subsolar levels. The presence of metals affects the lifetime through their role in stellar opacity. Higher metallicity produces higher opacity, which slows the rate of energy transport through the star. The lower energy transport rate slows the consumption of fuel, extending the lifetime. The specific calculations are complex, but the qualitative effect is that metal-rich low-mass stars live somewhat longer than the simple mass lifetime scaling would predict. No one expects, on first thinking about stellar lifetimes, that the longest-lived stars could persist for 10 million times the current age of the universe. No one predicts that any single object in the cosmos could continue to function as a steady nuclear fusion source for such enormously long durations. Absolutely no one anticipates the way the physics of low-mass stellar evolution produces such dramatic extensions of stellar lifetimes for objects at the lower end of the stellar mass range. The implications for the broader picture of cosmic stellar activity are substantial. The cosmic stellar activity does not end abruptly at any specific cosmic time. It tapers off gradually, with the rate of active stellar burning decreasing slowly as more and more stars exhaust their fuel. The very last active stars are not the same as the first stars or the typical stars of any specific epoch. They are specifically the lowest mass stars, with their extraordinarily long lifetimes, allowing them to outlast all the more massive stars of the various stellar generations. By the end of tonight, you're going to understand that the final star is, in this sense, the survivor of an enormously long elimination process. The high-mass stars of the early universe died first, exhausting their fuel within millions of years. The intermediate mass stars died over the following billions of years. The solar mass stars die over approximately 10 billion years. The low-mass red dwarfs die over hundreds of billions of years to trillions of years. The brown dwarf merger stars die last, with the very last one being the final star we are discussing tonight. Hold this image. The final star will burn for 10 trillion to 100 trillion years from its formation. The lifetime is enormously longer than any stellar lifetime that has actually been observed in the modern cosmos, because no star with such a long predicted lifetime has yet had time to complete it. The final star is, in this sense, both a real physical object, whose properties can be predicted from well-understood physics, and a categorical endpoint of cosmic stellar activity that we cannot directly observe. Before we walk into the third truth, take a slow breath here. The story is about to take a brief turn into a different kind of conversation. Tonight, we're going to walk through the specific physics of brown dwarf collisions that produce late stelliferous stars, because the merger mechanism is essential for understanding when the final star will actually form and what its properties will be. Before we get started, sit with what follows. The basic situation is this. Brown dwarfs are objects with masses below the minimum threshold for sustained hydrogen fusion. The minimum threshold is approximately 0.075 to 0.08 solar masses, depending on the specific composition. Objects below this threshold can briefly produce some nuclear fusion during their initial gravitational contraction, particularly through deuterium burning, but they cannot sustain proton-proton fusion long enough to qualify as proper stars. The brown dwarf population in the modern cosmos is uncertain, but is estimated to be approximately equal to the main sequence star population in numbers. The total brown dwarf population that will accumulate by the late stelliferous era will include all the brown dwarfs that have ever formed through standard stellar formation channels, plus the additional brown dwarfs produced through various binary stripping and migration processes during the cosmic history. By the end of tonight, you're going to understand that brown dwarfs occupy the same kinds of gravitational environments as proper stars. They orbit through galactic potentials, encounter each other through close passes, and occasionally undergo direct collisions. No one expects the brown dwarf rates to matter this much, but they do. The rate of brown dwarf collisions is very low for any specific brown dwarf, with the timescale for any single brown dwarf to experience a collision being approximately 10 to the 22nd years, much longer than even the cosmic age at the late stelliferous era. Pattern interrupt. But the cosmic time available during the late stelliferous era is enormously long, and the brown dwarf population is enormously large. The total number of brown dwarf collisions across cosmic history is therefore substantial, even though the rate for any specific brown dwarf is very low. The collisions provide the mechanism by which new stars continue to form long after the standard stellar formation channels have ended. The merger of two brown dwarfs produces a single object whose mass is approximately equal to the sum of the original two masses, with some material being lost through the violent dynamics of the collision. If the total mass exceeds the threshold for hydrogen fusion, the merger product will ignite sustained nuclear burning and become a small but proper star. The specific outcomes depend on the impact parameters, the relative velocities, and the masses of the original brown dwarfs. By the end of tonight, you're going to understand that not all brown dwarf collisions produce stars. Some collisions occur with masses below the fusion threshold and produce only a slightly more massive brown dwarf without igniting fusion. Other collisions produce mass ejection severe enough that the merger product is below the fusion threshold, even though the combined original mass was above it. The fraction of collisions that successfully produce stars depends on the specific mass distribution of the brown dwarf population and on the typical impact dynamics. The theoretical work on brown dwarf collision physics has been substantial. The leading calculations by various theoretical groups, including the work of Fred Adams and collaborators, suggest that approximately 10% of brown dwarf collisions successfully produce stars. The remaining 90% either produce non-stellar merger products or produce mass ejections severe enough to prevent stellar formation. Walk with me through what this implies for the rate of late stelliferous star production. The collision rate in any specific galaxy is determined by the brown dwarf population density and the typical relative velocities. The rate decreases over cosmic time as the brown dwarf population is depleted through previous collisions and through gravitational ejection from the galactic structure. The rate of successful star production is approximately 10% of the total collision rate. The specific numbers depend on the detailed assumptions, but the various theoretical estimates suggest that Milkomeda will produce approximately 10,000 merger-driven stars over the cosmic time up to 100 quadrillion years. The stars will form at progressively lower rates over time, with the very last successful merger event occurring perhaps 10 to the 17th years from the present, possibly slightly later. The final star, by every available calculation, will be one of these late merger products. The properties of the merger-produced stars depend on the specific collision dynamics. The merger product mass distribution is biased toward the low end of the stellar mass range, with most merger products having masses between 0.08 and 0.15 solar masses. The specific masses depend on the original brown dwarf masses and on the details of the collision. The final star, formed during the very last successful merger event, will likely have a mass near the absolute minimum for sustained fusion. No one expects, on first thinking about cosmic stellar formation, that the very last stars in the cosmos would be products of brown dwarf collisions rather than products of the standard stellar formation channels. No one predicts that the failed stars of the cosmic history, the brown dwarfs that never managed to ignite proper fusion, would eventually contribute to the very last stellar formation. Absolutely no one anticipates the way the cosmic stellar story has a specific ending that involves the merger of objects that were originally failures of the stellar formation process. The implications for the timing of the final star are substantial. The final star will form not at the conventional end of the cosmic stelliferous era at approximately 10 to the 14th years, but somewhat later during the early degenerate era, when the rate of brown dwarf collisions is still substantial enough to occasionally produce successful merger events. The specific cosmic time of the final star's formation depends on the detailed collision rate calculations, but the various estimates place it at approximately 10 to the 16th to 10 to the 17th years from the present. The final star will then burn for its full main sequence lifetime, which we have established to be approximately 10 trillion to 100 trillion years for a star at the minimum fusion threshold. The combination of the formation time and the lifetime places the eventual death of the final star at approximately 10 to the 17th years from the present, possibly slightly later. The specific value depends on the detailed assumptions, but the general range is consistent across the various theoretical analyses. By the end of tonight, you're going to understand that the final star is, in this sense, doubly defined by its mechanism of formation. It is the last successful brown dwarf merger event that produces a star, and it is the longest-lived star produced through that mechanism. The final star will be a specific object whose timing depends on the cosmic collision rate and whose properties depend on the specific collision dynamics. The various theoretical estimates converge on a final star with mass near the minimum fusion threshold, with formation time approximately 10 to the 17th years from the present, and with death time slightly later than the formation time, depending on the specific stellar lifetime. Hold this image. The final star will be the last successful product of an enormously long sequence of brown dwarf collisions. The collisions begin even during the current cosmic epoch, with some merger-driven stars being formed in the modern Milky Way. The collisions continue throughout the cosmic stelliferous era, with the rate gradually declining as the brown dwarf population is depleted. The very last successful merger occurs approximately 10 to the 17th years from the present, producing the final star. After that, no further successful mergers occur, and the brief dim star that has just formed is the last active stellar object in the entire cosmos. Before we continue, why this channel exists. If you have made it this far into a careful examination of the final star, you are not the casual viewer the platform expects. You are the person for whom this channel was built. Long-form cosmology, told at the pace of sleep, with enough technical detail to actually feel the weight of cosmic deep time, rather than just the headline summaries, is not what the algorithm rewards. It is what we make anyway, because we believe the cosmos is more interesting when the questions are developed carefully. If that resonates with you, the simplest thing you can do for the channel is to subscribe. Subscribing tells the platform that long, calm, careful work is worth surfacing for the next person who needs a quieter way to think about cosmic deep time. If you have already subscribed, thank you. Truly, if this is your first long-form night with the channel, welcome. A small additional note. If Spotify is where you find yourself on sleepless nights, consider following the show there. The audio versions are tuned for the same purpose, the same pace, the same care. Now, let us return to the cosmos. The third truth is waiting. The third truth is that the final star will die in essentially perfect silence. Tonight, we're going to walk through the specific physics of how very low-mass stars end their lives, because the death of the final star is one of the quietest events that can occur in cosmic physics, and the details deserve careful examination. The basic situation is this. The death of a star depends sensitively on its mass. Very massive stars, with masses above approximately 8 solar masses, end their lives in dramatic supernova explosions, with the stellar core collapsing into a neutron star or black hole and the outer layers being violently ejected into space. Intermediate mass stars between approximately 1 and 8 solar masses end their lives more gradually through the red giant phase, with the outer layers being shed into a planetary nebula and the core becoming a white dwarf. Low-mass stars, with masses below approximately 0.5 solar masses, end their lives even more gradually, without ever going through the red giant phase or producing any dramatic ejecta. The final star, at the absolute minimum mass for sustained hydrogen fusion, will follow the most gradual evolutionary path of any stellar object. The star will burn through its hydrogen at the slow, steady rate we discussed in the second truth. The convective mixing will continuously bring fresh hydrogen to the core for fusion, with the burning proceeding for the enormously long stellar lifetime. As the hydrogen is gradually consumed, the helium produced by fusion will accumulate throughout the star, with the mixing distributing the helium more or less uniformly. Notice that this gradual evolution has specific implications for the death of the final star. At some point, during the very late stages of its lifetime, the hydrogen abundance in the core will become low enough that the fusion rate begins to decrease. The decrease will be very gradual, with the burning rate declining slowly over the final stretch of the stellar lifetime. The star will not transition through any dramatic late evolutionary phases. It will simply continue to burn at progressively slower rates as its hydrogen supply gradually decreases. Pattern interrupt. The final stages of the star's life will be characterized by the gradual transition from active hydrogen burning to a state in which fusion is no longer occurring. The transition will happen over hundreds of millions of years at the very end of the stellar lifetime, with the star producing progressively less energy as its hydrogen supply approaches exhaustion. There will be no dramatic helium flash, no red giant phase, no planetary nebula ejection, no supernova explosion. The star will simply cool gradually as the nuclear reactions slow. The reason for this gradual death is the specific structure of very low-mass, fully convective stars. When the hydrogen supply in a more massive star is exhausted in the core, the star transitions to burning hydrogen in a shell around the now helium-rich core. The shell burning produces enough energy to inflate the outer layers, causing the star to expand into a red giant. The red giant phase eventually leads to either the ejection of the outer layers as a planetary nebula or to the collapse of the core into a supernova, depending on the stellar mass. For very low-mass stars, the full convection prevents the formation of a distinct helium core. The helium is distributed throughout the star rather than being concentrated in the center. There is no concentrated helium core to drive the transition to shell burning. There is no shell burning to inflate the outer layers. There is no red giant phase. The star simply remains a small main sequence object throughout its life, with the hydrogen abundance gradually decreasing through the cumulative effect of fusion over the enormously long stellar lifetime. What this picture tells us is that what happens to the final star at the very end? When the hydrogen abundance becomes too low to sustain active fusion, the star begins to contract under its own gravity. The contraction releases gravitational potential energy, which keeps the star warm for a while even though fusion is no longer occurring. The released energy is radiated away from the surface, with the star gradually cooling as the contraction proceeds. The contraction continues until the star is supported by electron degeneracy pressure rather than thermal pressure. At that point, the contraction stops and the star has effectively become a white dwarf. The transition from active main sequence star to white dwarf is, for the final star, essentially seamless. There is no dramatic event marking the moment when the star ceases to be a proper star and becomes a stellar remnant. The transition happens gradually over hundreds of millions of years at the very end of the stellar lifetime. Walk with me through what this looks like from the perspective of any potential observer alive during the death of the final star. The star, in its final years, would be a dim point of infrared light barely above the cosmic background. The radiation from the star would gradually decrease in intensity as the fusion slows and eventually stops. The star would continue to emit thermal radiation from its surface as it gradually cools, with the thermal emission decreasing over hundreds of millions of years as the surface temperature drops. There would be no specific moment when the death of the final star occurs. The transition from active hydrogen burning to inactive cooling is gradual, with the fusion rate declining smoothly over the final stretches of the stellar lifetime. Any observer trying to identify the specific moment when the final star died would face a definitional problem. The active burning rate declines continuously rather than dropping to zero suddenly. The convention would have to be established that the star is considered dead when the fusion rate drops below some specific threshold, with the threshold being somewhat arbitrary. No one expects, on first thinking about stellar deaths, that the death of the very last star in the cosmos would be such a gradual and undramatic event. No one predicts that the boundary between active stellar activity and the long quiet era that follows would be marked by a continuous transition rather than a sudden event. Absolutely no one anticipates the way the physics of low-mass stellar evolution produces such a gentle ending to the cosmic stelliferous epoch. The implications for the broader picture of cosmic transitions are substantial. The end of the stelliferous era is not a sharp boundary in cosmic time. It is a gradual transition over an extended period, with the active stellar activity gradually decreasing as more and more stars exhaust their fuel and as the rate of new, merger-driven stellar production declines. The death of the final star is the conventional marker for the end of the era, but the era effectively ends through a gradual decline rather than through any specific dramatic event. The contrast with the more dramatic events that occur during the stelliferous era is striking. The stelliferous era contains supernovae, gamma-ray bursts, magnetar giant flares, and various other dramatic events. The death of the final star is, in this sense, the opposite of these dramatic events. It is the quietest possible stellar ending, with no event distinct enough to register against the background of the cosmic environment. The cosmic transition from active stellar epoch to long quiet era is marked by silence rather than by drama. Tonight, we're going to walk through the specific reasons why the final star will not go through a red giant phase, because the absence of a red giant phase is one of the defining features of very low-mass stellar evolution, and the details are worth understanding carefully. The basic situation is this. The red giant phase is one of the most dramatic features of stellar evolution for intermediate mass stars. A star like the Sun, after exhausting the hydrogen in its core, transitions to burning hydrogen in a shell around the now helium-rich core. The shell burning produces enough energy to inflate the outer layers of the star, causing the star to expand by factors of approximately 100 in radius and decrease in surface temperature. The resulting object is the red giant, a large, dim, cool star that represents the late evolutionary stage of stars in the intermediate mass range. The red giant phase is dramatic and observationally distinctive. Red giants are common in the modern Milky Way, with many of the brightest stars visible to the naked eye being red giants. The Sun will eventually become a red giant approximately 5 billion years from now, expanding to a size that will engulf the inner planets of the solar system. Step back, and you can see that the red giant phase requires specific structural conditions in the star. The star must have a distinct helium core that is differentiated from the hydrogen-burning shell. The core must be supported by electron degeneracy pressure, with the hydrogen burning occurring in a shell at the boundary between the core and the outer envelope. The envelope must be convective, with the convective mixing transporting energy from the burning shell to the surface, where it can be radiated away. For stars below approximately 0.35 solar masses, including all the M dwarfs and brown dwarf merger stars, The structural conditions for a red giant phase do not apply. The star is fully convective throughout its interior, with convection extending from the surface all the way to the center. There is no distinct helium core. The helium produced by hydrogen fusion is distributed throughout the star by the convective mixing rather than being concentrated in the center. Pattern interrupt. Without a distinct helium core, the star cannot transition to shell burning. There is no boundary between a degenerate core and a burning shell, at which the shell burning could be sustained. The hydrogen continues to burn throughout the convective interior, with the burning rate gradually decreasing as the hydrogen supply is depleted. The star simply continues to burn at slower and slower rates until the hydrogen abundance becomes too low for any sustained fusion. The implications for the late evolutionary stages of low-mass stars have been worked out in considerable detail by theoretical groups. The leading calculations, including the work of Gregory Laughlin and his collaborators in the late 1990s, established that low-mass stars below approximately 0.25 solar masses simply transition from active main sequence burning to inactive white dwarf cooling without going through any intermediate red giant phase. The transition is gradual and continuous, with no specific moment marking the end of stellar activity. What becomes clear is that this has substantial implications for the death of the final star. The final star will not expand into a red giant. The final star will not eject a planetary nebula. The final star will not undergo a helium flash. The final star will not produce any of the dramatic late evolutionary events that characterize the deaths of more massive stars. The final star will simply cool gradually over hundreds of millions of years as its hydrogen supply approaches exhaustion. Now let's begin. The slow cooling produces specific empirical signatures that distinguish the late evolution of low-mass stars from the late evolution of more massive stars. The star's luminosity decreases gradually over the final stretches of its lifetime, with the decrease being approximately exponential over timescales of hundreds of millions of years. The surface temperature decreases in parallel with the radiation peak moving to progressively longer wavelengths as the cooling proceeds. The star never enters any specific late evolutionary phase that could be identified as distinct from the main sequence phase. Walk with me through what this implies for the empirical detection of the final star's death. If any observers exist at the cosmic moment of the final star's death and possess instruments capable of detecting the star, they would observe a gradual decrease in the star's brightness over enormously long time scales. There would be no specific event that they could identify as the death of the final star. The death would be a process rather than an event, with the transition from active stellar burning to inactive cooling being smooth and continuous. The convention in the theoretical literature is to consider the final star to have died when its luminosity has decreased below some specific threshold, typically taken as 1% of its main sequence luminosity. By this convention, the death of the final star occurs at a specific cosmic time that can be calculated from the stellar evolution models. But the choice of threshold is somewhat arbitrary, and other conventions would produce somewhat different specific times. The death of the final star is, in this sense, more of a categorical transition than a specific event. No one expects, on first thinking about stellar deaths, that the very last star in the cosmos would have such an undramatic ending. No one predicts that the boundary marker of the cosmic stelliferous era would be a slow, gradual cooling rather than a specific dramatic event. Absolutely no one anticipates the way the physics of low-mass stellar evolution combines to produce such a quiet ending to the cosmic active stellar epoch. The contrast with the deaths of more massive stars is striking. The deaths of high-mass stars produce supernova explosions, which are among the most dramatic events in the cosmos. The deaths of intermediate-mass stars produce planetary nebulae, which are visually striking and observable for thousands of years after the original event. The deaths of low-mass stars produce nothing observable beyond the gradual cooling. The cosmic stellar epoch begins with the dramatic births of the first stars and ends with the quiet fading of the final star, with the contrast between these two endpoints being one of the more poetic features of cosmic stellar history. The implications for the broader picture of cosmic transitions are substantial. The end of the cosmic stelliferous era is not marked by any specific dramatic event. The era effectively ends through the gradual fading of its last active stars, with no specific moment of transition that any observer could identify as the absolute end. The boundary between the active stellar epoch and the long, quiet aftermath is gradual rather than sharp, with the transition extending over hundreds of millions of years at the end of the final star's life. Hold this image. The final star will die quietly, with no dramatic event marking the moment of stellar death. The transition from active hydrogen burning to inactive cooling will be gradual and continuous. The cosmic stelliferous era will end through the slow fading of its last active star, with the long, quiet aftermath beginning without any specific identifiable boundary moment. The cosmic story has, in this sense, an ending that mirrors the slow build-up of cosmic stellar activity at the beginning. The cosmos begins with the first stars and ends with the last star, with the boundaries being gradual at both ends. Hold this image. The final star will die quietly. There will be no supernova explosion. There will be no planetary nebula ejection. There will be no dramatic phase transition. The star will simply cool gradually over hundreds of millions of years as its hydrogen supply approaches exhaustion. The transition from active main sequence star to inactive white dwarf will be smooth and continuous. The cosmic stelliferous epoch will end not with a bang, but with a long, slow fade. What emerges from this is that this is, in some sense, the most poetic feature of the death of the final star. The most dramatic events in cosmic physics happen during the active phases of cosmic history. The end of the active stellar epoch marked by the death of the final star happens in the quietest possible way. The cosmos does not announce the end of the stelliferous era. It simply lets the era fade out with no particular fanfare and no specific moment of transition. The fourth truth is that the final star will mark the absolute boundary of the cosmic stelliferous epoch. Tonight, we're going to walk through what this boundary actually means, because the transition from the active stellar epoch to the post-stelliferous cosmos is one of the most consequential events in the entire cosmic story. The basic situation is this. The stelliferous era is the era in which stars exist as active nuclear fusion sources. The era began approximately 100 million years after the Big Bang, when the first stars ignited. The era will continue until the very last active star exhausts its fuel and stops shining. After the final star dies, no other star will ignite anywhere in the cosmos, and the era will be over. The question of when this happens depends on several specific factors. The rate of brown dwarf collision events declines over cosmic time as the available brown dwarf population is depleted. The properties of brown dwarf merger products depend on the specific collision dynamics. The lifetimes of the merger-produced stars depend on their specific masses and metallicities. The combination of these factors determines when the last active stellar object will finally exhaust its fuel. The takeaway is that the various theoretical estimates place the death of the final star at approximately 10 to the 17th years from the present, possibly somewhat later. The specific value depends on the assumptions used in the calculation, but the general range is consistent across the various theoretical analyses. We are walking, in this sense, to a future moment that is approximately 10 million times the current age of the universe. Pattern interrupt. After the final star dies, no other star will ever ignite anywhere in the cosmos. The statement requires careful explanation. The cosmos will continue to contain large numbers of stellar remnants, including white dwarfs, neutron stars, and black holes. These remnants are not active stars in the sense of having ongoing hydrogen fusion. They are the cooled corpses of stars that have already exhausted their fuel. The cosmos will also continue to contain large numbers of brown dwarfs. These objects are not stars in the proper sense because they never sustained hydrogen fusion. They are slowly cooling objects that gradually radiate away the heat from their initial gravitational contraction. The brown dwarfs will continue to exist long after the final star dies, but they will not produce new stellar activity through any standard mechanism. The only mechanism by which new stars could form after the final star dies would be through additional brown dwarf collisions. The collisions could, in principle, continue producing merger objects with masses above the fusion threshold. But the rate of collisions declines steadily as the brown dwarf population is depleted through previous collision events and through gravitational ejection from galactic structures. At some specific cosmic time, the rate of collisions becomes so low that no further merger-driven stellar formation occurs in any meaningful sense. What this leaves us with is that the final star is, in this sense, the last surviving product of all the various stellar formation channels operating across cosmic history. Every other star that ever ignited has by then either died directly or been the parent of brown dwarfs whose merger products have died. The cosmic chain of stellar production, which began with the first population 3 stars approximately 100 million years after the Big Bang, ends with this single specific final stellar object approximately 10 to the 17th years from the present. The total cosmic duration of the stelliferous era is therefore approximately 10 to the 17th years, which is approximately 10 million times the current age of the universe. By the standards of cosmic time, the stelliferous era is enormously long. By the standards of the cosmic future, however, the stelliferous era is still relatively brief. The subsequent eras together will occupy enormously longer cosmic time than the entire stelliferous era ever did. Walk with me through what the cosmos will look like immediately after the death of the final star. The cosmos will contain approximately the same population of stellar remnants and brown dwarfs that we discussed in the previous truths. There will be no active stars producing fresh starlight anywhere. The most luminous objects in the cosmos will be the cooling stellar remnants, particularly the youngest white dwarfs that formed from the most recent stellar deaths. The white dwarfs will be cooling at rates determined by their masses and compositions, with the cooling continuing for enormously long subsequent cosmic time. The post-stelliferous cosmos will be much dimmer than the stelliferous cosmos. The current cosmic luminosity is dominated by the active stars, with each star producing energy through its nuclear fusion. The post-stelliferous cosmos will not have this active luminosity source. The cosmic luminosity will come entirely from the thermal radiation of the cooling stellar remnants and the various rare transient events that occasionally occur in the degenerate era. The transient events in the post-stelliferous cosmos include various processes we have discussed in other contexts. White dwarf binary mergers occasionally produce type Rya supernova explosions, which are dramatic events but very rare. Tidal disruption events at the central supermassive black hole produce bright, transient signatures, also rare. Black hole mergers produce gravitational wave signals but very little electromagnetic emission. The total rate of transient events in the post-stelliferous cosmos is much lower than the current cosmic rate, but the events do continue to occur at low rates throughout the degenerate era. No one expects, on first thinking about cosmic stellar activity, that the entire cosmic stellar epoch would end with a single specific final stellar object. No one predicts that the cosmic story would have such a clean, categorical boundary between the active stellar epoch and the long, quiet era that follows. Absolutely no one anticipates the way the cosmic physics produces such a specific and predictable endpoint for the stelliferous era. The implications for cosmic life are substantial. Life, as we know it, depends on active stellar processes. Stars provide the energy that powers planetary biospheres. The cosmic conditions for biological life as we currently understand it require active stellar fusion as the primary energy source. The death of the final star marks the end of the cosmic conditions for biological life of the current type. Whatever observers might exist in the post-stelliferous cosmos would need to operate on dramatically different energy budgets than current biological life uses. Some theoretical work has considered the possibility of life persisting into the post-stelliferous cosmos. The work, including the famous Freeman-Dyson analysis from 1979, suggests that suitable intelligence might be able to extend its survival into the degenerate era by progressively slowing down its metabolic processes to match the dramatically reduced energy availability. The persistent life would, in this picture, operate at progressively slower subjective rates as the cosmic conditions become progressively quieter. Whether any such life would actually persist is, of course, an open question. The end of cosmic biological activity is, in some sense, more important than the end of cosmic stellar activity. Stars exist, regardless of whether anyone is around to observe them, but biology requires specific cosmic conditions to operate. The death of the final star marks the end of those specific cosmic conditions in the most direct sense possible. From the moment of the final star's death onward, the cosmos will be operating in a regime that does not naturally support the kind of biological activity that has existed during the stelliferous era. Pattern interrupt. There is something genuinely strange about this. The cosmic moment when the final star dies is, in this sense, both a specific physical event and a categorical transition for the broader question of cosmic life. The transition is gradual rather than sudden, with the cosmic conditions becoming progressively less favorable for biological life as the active stellar population declines over the late stelliferous era. But the death of the final star marks the conventional boundary, the moment after which biological life would have to operate without any active stellar energy source. What surfaces from this is that the final star is, in this sense, more than just a specific stellar object. It is the marker of a cosmic transition. The transition is the boundary between the active cosmic epoch and the long quiet era that follows. The transition affects not just the stellar inventory, but also the broader picture of what kinds of physical processes can operate in the cosmos. The cosmic story changes fundamentally after the final star dies, with the subsequent eras being dominated by very different processes than those that have operated during the stelliferous era. Tonight, we're going to walk through what specifically happens to the cosmic environment in the period immediately after the final star dies, because the aftermath of the cosmic stelliferous era is one of the more concrete features of the deep cosmic future that we can predict in detail. The basic situation is this. Immediately after the death of the final star, the cosmos contains its full inventory of stellar remnants accumulated over the entire stelliferous era. The remnants include white dwarfs from the deaths of low-mass and intermediate-mass stars, neutron stars from the deaths of more massive stars, stellar mass black holes from the deaths of the most massive stars, and brown dwarfs that never managed to ignite proper fusion. The total population of these remnants in any specific galaxy is enormous, with the count being approximately equal to the total number of stars that ever formed in the galaxy. The dominant cosmic activity in the immediate post-stelliferous era is the continued cooling of these remnants. The cooling proceeds according to the specific physical laws that govern thermal radiation from each type of object. White dwarfs cool at the rates we discussed in the insert on white dwarf cooling. Neutron stars cool at somewhat different rates determined by the specific physics of their dense interiors. Brown dwarfs cool slowly as they radiate away the heat from their initial gravitational contraction. Black holes do not cool in the same sense, but they slowly lose mass through Hawking radiation at the extraordinarily slow rates determined by their masses. What follows from this is that the immediate post-stelliferous cosmos is, in this sense, defined by cooling. Every active process in the previous era involved nuclear fusion, producing fresh thermal energy. Every dominant process in the immediate post-stelliferous era involves the radiation of previously accumulated thermal energy. The cosmos transitions in this sense from a producer of fresh energy to a consumer of accumulated energy reserves. Pattern: interrupt. The cosmic luminosity decreases dramatically in the immediate post-stelliferous era. During the active stelliferous era, the cosmic luminosity is dominated by the active nuclear fusion in the various stars. The total cosmic luminosity during the active era is approximately 10 to the 47th watts, integrated across all the active stars in all the observable galaxies. After the death of the final star, the cosmic luminosity comes entirely from the cooling of stellar remnants and the various rare transient events. The total post-stelliferous luminosity is approximately 10 to the 37th watts, 10 orders of magnitude lower than the active era luminosity. The reduction in cosmic luminosity has implications for any observers who might exist in the post-stelliferous era. The night sky from any planet around any cooling stellar remnant would be substantially dimmer than the current night sky from Earth. The familiar stellar constellations would not exist because the stars that produce them have all died. The cosmic background would be much colder, having continued to cool from the expansion across the enormously long cosmic time. The visible cosmic environment would be one of pervasive dimness, with only the brightest cooling white dwarfs providing significant visible light sources. The rare transient events in the post-stelliferous era include processes we have discussed in other contexts: White dwarf binary mergers occasionally produce type Ia supernova explosions which briefly illuminate the surrounding cosmic environment with bright, transient signatures. Tidal disruption events at the central supermassive black hole of the local galactic structure produce bright, transient signatures with the disrupted matter heating up and accreting onto the black hole. Black hole mergers produce gravitational wave signals but very little electromagnetic emission. What this means is that the rate of these transient events declines rapidly with cosmic time during the post-stelliferous era. The white dwarf binary population is gradually depleted through previous merger events. The supply of stellar remnants on close orbits around the central supermassive black hole is depleted through previous tidal disruption events. The black hole binaries that can produce gravitational wave detectable mergers are depleted through previous merger events. The total rate of transient events declines steadily as the available reservoirs of merger candidates and disruption candidates are gradually used up. No one expects the cosmic structure to be so layered, but it is. Also continues to evolve in the post-stelliferous era. The galaxies, which were already largely depleted of their gas reservoirs during the late stelliferous era, continue to lose mass through various dynamical processes. Stellar remnants are gradually ejected from galaxies through gravitational interactions with other remnants. The ejected remnants drift through intergalactic space at low velocities, with the cosmic expansion further dispersing them over time. Walk with me through what this implies for the long-term evolution of Milkomeda after the death of the final star. The galaxy will gradually become more diffuse over enormously long cosmic time, with the bulk of its stellar remnants being ejected into intergalactic space. The central concentration around the supermassive black hole will become a more dominant fraction of the total remaining galactic mass, with the outer regions being progressively depleted. By approximately 10 to the 20th years from the present, the bulk of the galactic structure will have been dispersed, with only the central concentration remaining as a coherent system. The central concentration will continue to evolve through subsequent cosmic time. The supermassive black hole will continue to accrete the stellar remnants that pass close enough to it, with the mass of the black hole gradually increasing. By the end of the degenerate era, at approximately 10 to the 39th years from the present, the original galactic structure will have been essentially completely dispersed, with the supermassive black hole being the only major surviving feature. No one expects, on first thinking about cosmic deep time, that the cosmic environment in the immediate post-stelliferous era would be so well defined by the slow processes of cooling and gradual structural dispersion. No one predicts that the cosmos after the death of the final star would continue to evolve in such specific, predictable ways across enormously long cosmic time. Absolutely no one anticipates the way the immediate post-stelliferous era contains so much specific cosmic content despite the absence of active stellar processes. The implications for understanding the death of the final star are substantial. The final star's death is not just the end of an individual stellar object, it is the marker of the transition to the long, quiet era in which the cosmic environment is dominated by cooling and gradual dispersion rather than by active stellar fusion. The transition is, in this sense, more consequential than the individual stellar death suggests, with implications for the entire subsequent cosmic history. The implications for any potential observers in the post-stelliferous era are also substantial. The cosmic environment they would observe is fundamentally different from the cosmic environment we currently observe. The processes that dominate cosmic activity are different. The luminosity sources are different, the available energy reservoirs are different. Any observers alive in the post-stelliferous era would need to develop fundamentally different cosmological frameworks than the frameworks we currently use, with the differences reflecting the different cosmic conditions they inhabit. Hold this image. The immediate post-stelliferous cosmos is defined by cooling. Stellar remnants cool at the rates determined by their specific physics. The cosmic luminosity is dramatically lower than in the active stelliferous era. The transient events occur at progressively lower rates as the reservoirs of merger candidates are depleted. The galactic structures gradually disperse through dynamical processes. The cosmic environment evolves slowly toward the eventual transition to the black hole era, with the dispersal of galactic structures and the cooling of stellar remnants being the dominant processes throughout the degenerate era. The cosmic story continues, but at a fundamentally different tempo than the active era that preceded the death of the final star. Hold this image. The final star is the boundary marker of the cosmic stelliferous epoch. After the final star dies, the cosmos enters a new regime in which active stellar fusion no longer provides the dominant energy source. The transition is gradual, but the boundary is real. The cosmic story has, in this sense, a beginning, a middle, and an end for its active stellar phase. The end is marked by the death of this one specific star, approximately 10 to the 17th years from the present. The fifth truth is the one that puts the death of the final star into the broader context of cosmic time. Tonight, we're going to walk into this carefully because the comparison between the duration of the cosmic stelliferous epoch and the duration of the cosmic future after the final star dies is one of the most striking features of the deep cosmic future. The basic situation is this. The cosmic stelliferous era has a total duration of approximately 10 to the 17th years, from the formation of the first stars at approximately 10 to the 8th years, after the Big Bang to the death of the final star at approximately 10 to the 17th years from the present. The cosmic future after the death of the final star will continue, by every available calculation, for enormously longer than this. The degenerate era will continue from approximately 10 to the 17th years until approximately 10 to the 39th years. The duration of the degenerate era is therefore approximately 10 to the 22nd times longer than the stelliferous era. By the standards of cosmic time, the degenerate era is enormously longer than the entire stelliferous epoch that preceded it. The point worth taking away is that the black hole era will continue from approximately 10 to the 39th years until approximately 10 to the 100th years. The duration of the black hole era is approximately 10 to the 61st times longer than the degenerate era and approximately 10 to the 83rd times longer than the stelliferous era. By any meaningful standard of cosmic time, the black hole era is the dominant phase of the cosmic future. Pattern interrupt. The dark era will begin after the last black hole evaporates and will continue indefinitely. The dark era has no defined end. The duration of the dark era, considered as the total subsequent cosmic time, is therefore unbounded. Even if we restrict our attention to the predictable physics of the next 10 to the 200th years or so, the dark era duration is far longer than the combined duration of all the previous eras. The cumulative ratio between the cosmic time after the death of the final star and the duration of the stelliferous epoch is approximately 10 to the 83rd, or more depending on how one accounts for the dark era duration. The number is, in any meaningful sense, beyond ordinary comprehension. The vast majority of cosmic time is in the era after the final star dies. To put this into perspective, consider the relative durations of various cosmic phases. The current cosmic age is approximately 10 to the 10th years. The duration of the stelliferous era is approximately 10 to the 17th years, which is approximately 10 million times the current cosmic age. The duration of the cosmic future after the death of the final star is approximately 10 to the 100th years or more, which is approximately 10 to the 83rd times the duration of the stelliferous era. The ratio between cosmic future and cosmic stelliferous epoch is itself approximately 10 to the 83rd, which means the cosmos will spend approximately 10 to the 83rd times more time in the dark post-stelliferous state than in the lit stelliferous state. Notice that this means the cosmos we observe today is, in a precise sense, atypical of the cosmos that will exist for most of cosmic time. The active stellar epoch we currently inhabit is a brief and unusual phase of cosmic history. The configurations we observe daily, including the active stars and the visible galaxies in the cosmic web, are characteristic of only a tiny fraction of cosmic time. The vast majority of cosmic time will be characterized by configurations very different from what we currently observe. The implications for thinking about cosmic typicality are substantial. Most observers, if they exist across cosmic time, would be observing dark cosmoses rather than lit cosmoses. The lit cosmos is, in this sense, a rare configuration whose particular features depend on the specific moment of cosmic history. The dark cosmoses that follow will continue for enormously longer than the lit cosmos ever lasted, with the cosmic features being characterized by stellar remnants, black holes, and eventually individual particles drifting through empty space. Walk with me through the implications for how to think about cosmic value. The cosmos we observe is the cosmos during its brief, active phase. The richness of cosmic structure we currently access depends on our specific moment in cosmic time. Future observers, separated from us by enormous cosmic intervals, would inherit dramatically less rich cosmic configurations. The current moment is, in this sense, a particularly valuable time for cosmic observation, with the value being a function of the specific cosmic epoch. The empirical observations being made by current cosmologists are observations of a configuration that will not be available to any future observer in our region of space. The work is, in this sense, more time-sensitive than ordinary scientific work. The current cosmic moment is approximately 10 to the 83rd times shorter than the eventual cosmic future, which means we are working with proportionally limited cosmic time to make our observations of the active cosmic configuration. The work has a particular cosmic urgency that future cosmic work will not have. No one expects, on first thinking about cosmic time, that the active stellar epoch would be such a small fraction of total cosmic history. No one predicts that the cosmos would spend so much more time in the dark, post-stelliferous state than in the lit stelliferous state. Absolutely no one anticipates the way the cosmic future contains so much more time than the cosmic past and present combined. The implications for thinking about cosmic stories are substantial. The cosmos has in some sense a structure with a beginning, a middle, and a long aftermath. The beginning is the Big Bang and the early hot, dense phase. The middle is the active stellar epoch, the time during which the cosmos is rich with luminous structure and during which planetary life can flourish. The aftermath is the enormously long quiet phase after the active stellar epoch ends, during which the cosmos slowly transitions through the degenerate era, the black hole era, and the dark era. The structure of the cosmic story is, in this sense, weighted toward the aftermath. The middle phase, which contains essentially all the cosmic activity we currently observe, is enormously shorter than the aftermath. The cosmic narrative, considered across its full temporal extent, is dominated by the long, quiet phase rather than by the brief active phase. The active phase is, by every available measurement, the exception rather than the rule. What this picture tells us is that this is, in some sense, the deepest implication of the final star truth. The cosmic story has a brief active middle and an enormously long, quiet aftermath. The final star marks the boundary between these two phases. The death of the final star is, in this sense, the most consequential single event in the cosmic story, marking the end of the brief active phase and the beginning of the long, quiet aftermath. There is something philosophically substantial about this. The active cosmos we observe is genuinely temporary. The quiet cosmos that will follow is enormously longer lasting. The cosmic structure is weighted toward the quiet phase. We are alive during the brief, active middle, with all the empirical richness that this provides. The richness will not last, in the sense that the cosmic configuration that produces it will eventually end. The final star marks the moment when the richness ends. Pattern interrupt. There is no need to feel sad about this. The brief, active phase is, while temporary, genuinely valuable. The cosmic configuration we currently observe is genuinely rich. The empirical observations we are currently making are genuinely productive. The fact that this configuration will eventually end does not diminish its current value. The cosmic story, taken across its full temporal extent, has a particular shape, and we are alive during a particular phase of that shape. The shape itself is genuinely interesting, with both the brief active middle and the enormously long quiet aftermath being real features of the cosmic story. Tonight, we're going to walk through specific cosmic time comparisons that help put the death of the final star into perspective, because the timescales involved are so far beyond human experience that careful comparisons are necessary to understand what they actually mean. The basic situation is this. The cosmic time we are discussing involves numbers that are far beyond ordinary human framing. The death of the final star occurs at approximately 10 to the 17th years from the present. The end of the degenerate era occurs at approximately 10 to the 39th years. The end of the black hole era occurs at approximately 10 to the 100th years. The dark era continues indefinitely. The various ratios between these timescales involve quantities that no human framework can really hold. Useful comparisons help. Consider the ratio between the cosmic time after the death of the final star and the duration of the cosmic stelliferous era. The duration of the stelliferous era is approximately 10 to the 17th years. The duration of the cosmic future after the final star dies, taken to the end of the black hole era, is approximately 10 to the 100th years. The ratio is approximately 10 to the 83rd. Step back, and you can see that what this ratio actually means in concrete terms. If the entire stelliferous era were compressed into 1 second, the cosmic future after the death of the final star would correspond to approximately 10 to the 83rd seconds. In ordinary human terms, this is approximately 10 to the 75th years, which is enormously longer than the actual cosmic future being represented. The comparison breaks down because the ratio is so large that no human framework can hold both sides. Sit with this. Another way to think about this is to compare the cosmic stelliferous era to a single human lifetime. The current cosmic age is approximately 10 to the 10th years. A human lifetime is approximately 100 years. The ratio of cosmic age to human lifetime is approximately 10 to the 8th. The cosmic time after the death of the final star taken to the end of the black hole era is approximately 10 to the 90th times the current cosmic age. Compared to a human lifetime, the cosmic future after the death of the final star is approximately 10 to the 98th times longer than a human lifetime. The number is, in any meaningful sense, beyond comprehension. No human framework can hold quantities of this magnitude. The cosmic future is, in a very strict mathematical sense, enormously larger than the cosmic past and present combined. The brief, active stellar epoch we currently inhabit is, by these comparisons, approximately as significant a fraction of cosmic history. As a single fundamental particle, interaction is a significant fraction of the entire history of the cosmos. The cosmic future dwarfs the cosmic past by factors that exceed any meaningful scale of comparison. Walk with me through one specific implication. Consider the relative weight of cosmic time in the active stellar epoch versus the cosmic time after the death of the final star. The active stellar epoch contains approximately 10 to the 23rd stars that have ever ignited across cosmic history. The cosmic time after the death of the final star contains, by every available calculation, no active stars at all. The ratio of stellar count to cosmic time during the active epoch is approximately 10 to the 23rd over 10 to the 17th, which is approximately 10 to the 6th. The ratio of stellar count to cosmic time during the post-stelliferous era is 0 over 10 to the 83rd, which is 0. The implication is that the active stellar epoch represents the only cosmic era during which stellar formation occurs. The cosmic stars are not distributed uniformly across cosmic time. They are concentrated in the brief, active middle of cosmic history. The rest of cosmic time, both before the stelliferous era and after it, is essentially without stars. The cosmic stellar inventory is, in this sense, an artifact of a specific, brief, cosmic epoch rather than a continuous feature of cosmic time. What becomes clear is that this has implications for thinking about cosmic typicality. The cosmic configurations we observe are characteristic of the active stellar epoch. The configurations are not typical of cosmic time taken in its entirety. The vast majority of cosmic time involves configurations that are fundamentally different from anything we currently observe. The current cosmic configuration is, in this strict statistical sense, atypical. The implications for any potential observers across cosmic time are substantial. Most observers, if they exist across cosmic time, would be observing dark cosmoses rather than lit cosmoses. The lit cosmos is, in this sense, a rare configuration whose specific features depend on the active stellar epoch. The observers alive during the post-stelliferous era, if any exist, would observe a cosmos that is fundamentally different from the cosmos we currently observe. The empirical implications for the current generation of cosmologists are interesting. The current cosmic configuration is genuinely rare in the broader cosmic context. The empirical observations being made now are observations of a rare configuration that will not be available to most cosmic observers across the long cosmic future. The work has, in this sense, a particular value that comes from being conducted during a particularly empirically productive cosmic moment. No one expects, on first thinking about cosmic time, that the cosmic future would be so dramatically larger than the cosmic past and present combined. No one predicts that the brief active stellar epoch would be such a small fraction of total cosmic history. Absolutely no one anticipates the way the cosmic temporal structure is weighted so heavily toward the long, quiet aftermath, rather than toward the active stellar middle. The philosophical implications are substantial. The cosmic story has a specific temporal structure, with the active middle being enormously shorter than the long aftermath. The story is, in this sense, weighted toward the aftermath rather than toward the middle. The active middle, which contains essentially all the cosmic activity we currently observe, is the brief exception rather than the long rule. The cosmic narrative, taken across its full temporal extent, is dominated by the long quiet phase rather than by the brief active phase. There is something genuinely strange about this. The cosmic configuration we observe daily is, in the broader cosmic context, the rare exception rather than the common rule. The active stars, the visible galaxies, the rich cosmic web are all characteristic of only the brief, active middle of cosmic history. The much longer aftermath will be characterized by configurations without active stars, without rich cosmic web, without the empirical richness we currently access. What emerges from this is that this implies something specific about the current cosmic moment. We are alive during a particularly valuable cosmic time, in the sense that the configurations we observe are characteristic of only this brief phase of cosmic history. The empirical work we are currently doing has a particular cosmic value that future empirical work will not have. The cosmic moment we inhabit is, by every available measurement, both extraordinary and temporary. Hold this image. The cosmic future, after the death of the final star, is approximately 10 to the 83rd times longer than the cosmic stelliferous era. The numbers are beyond comprehension. The implications are that the active stellar epoch is the rare exception in the broader cosmic story. The cosmic configurations we observe are characteristic of only this brief active phase. The cosmic story is weighted toward the long, quiet aftermath rather than toward the brief active middle. We are alive during the rare exception, with the corresponding empirical privileges and the corresponding temporal urgency that this implies. Hold this image. The cosmos will spend approximately 10 to the 83rd times more time in the dark post-stelliferous state than in the lit stelliferous state. The cosmic story is weighted toward the long, quiet aftermath rather than toward the brief active middle. The death of the final star marks the boundary between these two phases. We are alive during the brief active phase with all the empirical richness this provides. The cosmic story is, by every available indication, far longer than its brief active middle suggests, with the bulk of cosmic time being in the era after the final star has died. The takeaway is that the fifth truth is, in this sense, the most important of the five. The death of the final star is not just the end of a specific stellar object. It is the end of the cosmic active phase, marking the transition to the enormously long aftermath. The cosmic story, considered carefully, is dominated by what happens after the final star dies. The active phase we currently inhabit is the brief exception that precedes the long rule. Tonight, we're going to spend a careful pass on what the final star implies for the broader picture of cosmic stellar activity, because the death of the final star marks a categorical boundary that has implications across multiple aspects of cosmic physics. Before we get started, sit with the basic framework. The cosmic stelliferous era has lasted, by the moment of the final star's death, for approximately 10 to the 17th years. During that era, stars have ignited, lived their lives, and died across an enormous range of timescales depending on their masses. The most massive stars lived briefly and exploded as supernovae. The intermediate mass stars lived for billions to tens of billions of years and ended as white dwarfs. The lowest mass stars lived for trillions of years and ended as white dwarfs without going through dramatic late evolutionary stages. The cumulative effect of all these stellar lives is the cosmic chemical inventory we currently observe. The first generations of stars, the population 3 stars composed only of hydrogen and helium, produced the first heavy elements through their supernovae. Subsequent generations of stars inherited the enriched chemical composition and further enriched it through their own stellar evolution. The chemical evolution of the cosmos has been a gradual progression from pure hydrogen and helium to the rich chemical composition that includes essentially all the elements of the modern periodic table. What this leaves us with is that the final star is, in this sense, the end point of an enormously long chemical evolution process. Its composition reflects the cumulative chemical enrichment from all previous stellar generations. Its mass, near the absolute minimum for sustained fusion, places it at the small end of the stellar mass distribution. Its formation, through brown dwarf merger, reflects the specific dynamical conditions of the late stelliferous era. The final star is, in every relevant sense, the product of an enormously long cosmic history. Take a slow breath here. The death of the final star is, in this sense, the end of a process that began with the formation of the first stars approximately 10 to the 8th years after the Big Bang. The process has continued for approximately 10 to the 17th years, with stars of various masses contributing to the cosmic chemical inventory and to the broader structural development of the cosmos. The end of the process is the end of the cosmic chain of stellar production that began with the first stars. The implications for cosmic chemistry are substantial. The cosmic chemical inventory will not continue to evolve after the death of the final star. The cosmic abundance pattern, which has been gradually shifting toward higher heavy element content throughout cosmic history, will essentially freeze at the levels achieved by the end of the stelliferous era. The white dwarfs, neutron stars, and black holes that remain after the death of the final star will carry the chemical fingerprint of the cumulative stellar evolution that produced them, but they will not produce any further chemical evolution. The implications for the broader picture of cosmic life are also substantial. Life as we know it depends on the chemical inventory that cosmic stellar evolution has produced. The complex molecules that form the basis of biology require carbon, nitrogen, oxygen, and various other heavy elements that the stars have forged through nuclear fusion. The chemical inventory will not continue to grow after the death of the final star, which means the available material for any subsequent life will be limited to what the cosmic stellar evolution has already produced. What surfaces from this is that this has implications for thinking about cosmic life across cosmic time. Life can, in principle, persist into the post-stelliferous era, but it would have to operate on the chemical inventory inherited from the previous era. The inventory is rich in the sense that the stelliferous era has produced essentially all the elements that biology needs, but the inventory is limited in the sense that no further chemical evolution will produce new elements or change the relative abundance patterns. Walk with me through one specific implication for the broader picture of cosmic stellar activity. The cosmos has, in its cumulative stellar activity, produced approximately 10 to the 23rd stars across the entire stelliferous era. The cumulative cosmic energy output from all these stars is approximately 10 to the 75th ergs, integrated over the full duration of the stelliferous era. This is, by every available measurement, the dominant source of cosmic luminosity across the active stellar epoch. The total cosmic energy output from all subsequent processes after the death of the final star is much smaller than the stelliferous energy output. The remnant cooling, the Hawking radiation from black holes, the rare transient events, all together produce only approximately 10 to the 65th ergs over the enormously long subsequent cosmic time. The cosmic energy budget is therefore dominated by the active stellar epoch, with the post-stelliferous era contributing only a small fraction of the total. No one expects, on first thinking about cosmic energy budgets, that the brief active stellar epoch would dominate the total cosmic energy output across all of cosmic time. No one predicts that the enormously long post-stelliferous era would contribute only a small fraction of the total cosmic energy. Absolutely no one anticipates the way the cosmic energy story is so heavily weighted toward the brief active middle rather than toward the long quiet aftermath. Expectation? The long cosmic future produces enormous amounts of cumulative energy because of its enormous duration. Reality. The long cosmic future produces only a small fraction of the cosmic energy because the active processes during that future are so much less energetic than the active stellar processes of the brief stelliferous era. The implications for thinking about cosmic value are interesting. The cosmic energy output, considered as a measure of cosmic activity, is concentrated in the brief active middle. The cosmic future, despite its enormous duration, contributes only modestly to the total cosmic energy budget. The brief active middle is, in this sense, the cosmic moment of greatest activity, with the cosmic future being a long, quiet aftermath that follows. What follows from this is that this is part of why the death of the final star is so consequential. It marks the end of the cosmic active phase, the phase during which essentially all the cosmic activity occurs. After the death of the final star, the cosmos enters a regime of dramatically reduced activity, with the subsequent cosmic processes operating at fundamentally lower energy budgets than the active stellar epoch did. There is something genuinely poignant about this. The cosmic active phase is the phase of cosmic richness. The cosmic processes during the active phase are responsible for essentially all the cosmic structure, all the cosmic chemistry, all the cosmic conditions for biology. After the active phase ends, marked by the death of the final star, the cosmos transitions into a regime of slow decay, rather than active creation. The cosmic story, considered across its full extent, has a structure of brief active richness, followed by enormously long slow decay. Hold this thought. The cosmic active phase is, in this sense, the phase of cosmic life. The cosmic chemistry, the cosmic structure, the cosmic conditions for biology all develop during the active phase. The brief active middle of cosmic history contains essentially all the cosmic richness. The long quiet aftermath inherits the richness but does not extend it. The cosmic story is, in this respect, a story of brief creative activity followed by enormously long inheritance and slow decay. What this leaves us with is a sense of why the death of the final star matters beyond the specific stellar object. It marks the boundary between the cosmic creative phase and the cosmic inheritance phase. The cosmos before the death of the final star is creating, through active stellar processes, the richness that defines the cosmic story. The cosmos, after the death of the final star, is inheriting that richness and slowly losing it through various processes of decay and dispersion. The transition between these two phases is, in this sense, the most consequential cosmic transition that we can specifically predict from current physics. Tonight, we're going to address 5 common misconceptions about the final star directly, because each one is widely repeated in popular discussion, and each one deserves a careful correction. Now, let's begin with the first misconception. The misconception is that the final star will die in a dramatic event. The claim sometimes appears in popular contexts that depict the death of the final star as a supernova explosion or some other dramatic phenomenon. The technical reality is the opposite. The final star will be at the absolute minimum mass for sustained fusion. It will not have the structural conditions required for a supernova explosion. It will not have the structural conditions required for a planetary nebula ejection. It will simply cool gradually as its hydrogen supply approaches exhaustion. The death will be one of the quietest possible stellar endings. No one expects, on first hearing the popular framing, that the gap between the popular dramatic version and the technical undramatic version could be quite this large. No one predicts that the most widely repeated interpretation of the final star would so substantially mischaracterize the actual physics. Absolutely no one anticipates the way the popular discussion has compressed a quiet, gradual cosmic transition into a dramatic narrative event. Before we get started on the second misconception, sit with why the first one persists. Dramatic events are intuitive and memorable. Gradual transitions are harder to convey in popular contexts. The popular framing has, predictably, favored the dramatic version, even though it does not match the actual physics. Now, let's begin with the second misconception. The misconception is that the final star will be the last surviving object in the cosmos. The claim sometimes appears in popular contexts that depict the death of the final star as the end of cosmic content more broadly. The technical reality is more measured. The death of the final star marks the end of active stellar fusion, but it does not mark the end of cosmic content. The cosmos will continue to contain stellar remnants, brown dwarfs, and black holes for enormously longer than the entire stelliferous era ever lasted. The final star is the last active star, but it is far from the last object in the cosmos. What this means is that this distinction matters. The popular framing of the final star as the absolute end of cosmic structure is technically incorrect. The cosmic structure continues for enormously longer than the stelliferous era, with the various remnants and brown dwarfs and black holes persisting through the degenerate era and the black hole era. The death of the final star is a specific transition, but not the absolute end of cosmic content. The third misconception is that the final star will be visible to any current observer. The claim sometimes appears in popular contexts that depict the final star as an object we could potentially observe, or that future generations might observe directly. The technical reality is that the final star will not form for approximately 10 to the 17th years from the present, which is enormously longer than any plausible human timescale. The final star is, in this sense, a theoretical object whose properties we can predict from physics, but whose actual existence is in the deep cosmic future. Expectation. The final star is an observable astronomical object. Reality. The final star is a theoretical prediction whose actual existence is in the deep cosmic future, with no plausible observational possibility for any human observer. The fourth misconception is that the death of the final star will mark the end of cosmic processes. The claim sometimes appears in popular contexts that depict the post-stelliferous cosmos as static, or essentially dead. The technical reality is that the cosmos will continue to undergo various physical processes after the death of the final star. The cooling of stellar remnants will continue. The occasional brown dwarf mergers may continue at lower rates. The white dwarf binary mergers will continue to produce occasional type Ia supernovae. The black holes will continue to slowly lose mass through Hawking radiation. The cosmic processes are different from the active stellar processes, but they are not absent. No one predicts, on first thinking about cosmic deep time, that the post-stelliferous cosmos would continue to contain such specific, predictable processes despite the absence of active stellar fusion. No one expects that the cosmic activity would continue at reduced but non-zero rates throughout the long aftermath. Absolutely no one anticipates the way the post-stelliferous era retains its specific empirical content, despite being dominated by slow processes rather than by dramatic active phenomena. Notice the turn. The fifth misconception is that the final star is fully understood. The claim sometimes appears in confident popular discussions that present the predictions as complete and certain. The technical reality is that substantial uncertainties remain. The specific brown dwarf collision rates are uncertain. The specific lifetimes of merger products depend on details that are not fully constrained. The role of dark energy in shaping the cosmic environment at the relevant future times is uncertain. The various theoretical estimates produce a range of specific predictions rather than a single definitive answer. The point worth taking away is that this is part of why the final star research continues to be active. The basic framework is well established, but the specific details are subject to ongoing refinement as the underlying physics is better understood. The work continues with substantial expected refinement over the coming years as the various uncertainties are progressively addressed through theoretical and computational work. Hold this image: 5 misconceptions, each one widely repeated, each one wrong in specific ways. The corrections do not diminish the significance of the final star as a research topic. The object is genuinely real in the sense that it is a specific theoretical prediction that follows from well-understood physics. The timing of its formation and death are genuinely consequential, marking the boundary of the cosmic stelliferous era. The implications for the broader picture of cosmic time are genuinely substantial, but the popular framings, while attention-grabbing, do not accurately represent the technical situation. What this leaves us with is a clearer view of what the final star actually means, not a dramatic event, not the absolute end of cosmic content, not an observable astronomical object, not the end of cosmic processes, not fully understood in all details. Expectation, the popular framing. Reality, the actual situation is more measured, more interesting, and in some ways more honest than any of the popular framings suggest. The final star is a theoretical prediction whose properties can be calculated from well-understood physics, marking a specific cosmic transition that has substantial implications for the broader picture of cosmic time, but that does not match the dramatic depictions sometimes encountered in popular discussions. Tonight, we're going to spend a careful pass on what comes after the death of the final star, because the cosmic future continues for enormously longer than the brief active middle, and the subsequent epochs are worth understanding in some outline. Now, let's begin with the immediate aftermath. After the death of the final star, the cosmos enters the degenerate era proper. The era will continue from approximately 10 to the 17th years until approximately 10 to the 39th years. During this enormously long stretch, the cosmic environment is dominated by the cooling of stellar remnants and by the gradual dispersion of galactic structures through various dynamical processes. The dominant processes during the degenerate era include the continued cooling of white dwarfs toward thermal equilibrium with a cosmic background, the slow gravitational ejection of stellar remnants from galactic potentials, the gradual accretion of stellar remnants onto central, supermassive black holes, and the possible decay of protons through processes predicted by some grand, unified theories. Each of these processes operates on its own characteristic timescale, with the combined effect being the gradual transformation of the cosmic environment from the stelliferous configuration to the configuration that will eventually characterize the black hole era. Notice that the black hole era begins when only black holes remain as significant cosmic structures. The era will last from approximately 10 to the 39th years until approximately 10 to the 100th years. During this era, the cosmos will be populated exclusively by black holes of various masses, slowly evaporating through Hawking radiation over the enormous timescales we discussed in the insert on Hawking physics. Step back. The dark era will begin after the last black hole evaporates and will continue indefinitely. The dark era will be characterized by individual particles drifting through essentially empty space, with no significant cosmic structures of any kind remaining. The cosmic time available for this final era is in principle unbounded, with the cosmos continuing to exist in this state for as long as the underlying physics allows. The role of the final star in this broader cosmic future is, in some sense, foundational. The death of the final star marks the beginning of the long sequence of subsequent cosmic transitions. Without the final star to mark the end of the stelliferous era, there would be no defined boundary between the active phase and the quiet aftermath. The final star is, in this sense, the cosmic timestamp for the transition between the brief, active middle of cosmic history and the enormously long, quiet aftermath that follows. What this picture tells us is that the various cosmic eras after the death of the final star have their own characteristic processes and their own characteristic timescales. The degenerate era is characterized by remnant cooling and structural dispersion. The black hole era is characterized by Hawking evaporation. The dark era is characterized by particle drift through essentially empty space. Each era operates on its own physics and produces its own cosmic configurations. Walk with me through one specific implication for the broader cosmic story. The cosmic time after the death of the final star is enormously longer than the brief, active middle that preceded it. The various subsequent eras together span approximately 10 to the 83rd times longer than the cosmic stelliferous era. The cosmic story, taken across its full temporal extent, is dominated by the long, quiet aftermath rather than by the brief, active middle. The implications for cosmic typicality, which we have discussed in other contexts, are substantial. Most cosmic time is spent in the dark, post-stelliferous state. The active stellar epoch is the rare exception in the broader cosmic context. The configurations we observe in the modern cosmos are characteristic of this rare exception rather than of the cosmic time taken as a whole, Future cosmologists, if any exist at substantially later cosmic times, will work with much smaller data sets than we currently have access to. No one expects, on first thinking about the cosmic future, that the various subsequent eras would together span enormously longer cosmic time than the brief active middle. No one predicts that the cosmic story would have such a dramatic temporal weighting toward the long, quiet aftermath. Absolutely no one anticipates the way the cosmic temporal structure places the brief active middle as the rare exception in an enormously long cosmic story. The empirical detection of the various subsequent eras is, by every available indication, far beyond any plausible human timescale. The degenerate era will not begin until enormously longer than any human civilization could plausibly persist. The black hole era will not begin until enormously longer than the eventual heat death of any plausible biological observer. The dark era will not begin until enormously longer than even the most generous estimates of how long any post-biological intelligence might persist. The subsequent eras are in this sense beyond any plausible observational possibility. Step back, and you can see that this is part of why the deep cosmic future is so interesting as a topic of theoretical research. The eras cannot be directly observed by any plausible future observer. They can only be predicted from current physics. The predictions are testable in principle in the sense that they follow from well-understood physical laws that have been verified in current cosmic observations, but the predictions cannot be directly checked through any feasible observational program. The implications for the broader picture of cosmic empirical accessibility are substantial. The active stellar epoch we currently inhabit is empirically rich, with the current cosmic configuration being directly observable through our instruments. The subsequent eras are not empirically accessible to any plausible observer. The cosmic empirical accessibility is, in this sense, concentrated in the brief active middle, with the long aftermath being theoretically predictable but empirically inaccessible. Hold this image. The cosmic future continues for enormously longer than the brief active middle that contains the death of the final star. The various subsequent eras together span approximately 10 to the 83rd times longer than the cosmic stelliferous era. The eras are theoretically predictable but empirically inaccessible. The cosmic story is dominated in its full temporal extent by the long aftermath rather than by the brief active middle. The death of the final star is the boundary marker between these two phases, with the brief active phase being the rare exception that produces essentially all the cosmic activity, and the long aftermath being the much longer rule that follows. What becomes clear is that this is part of what makes the final star so consequential. It is the boundary marker for the most important cosmic transition we can specifically predict from current physics. The cosmic story has, in this sense, a specific temporal structure with a brief active middle and an enormously long, quiet aftermath. The final star marks the boundary between these two phases. The cosmic story, considered carefully, is the story of the brief active middle followed by the enormously long, quiet aftermath that comes after the final star dies. What this leaves us with is a sense of why the deep cosmic future is so consequential as a topic. The future is enormously longer than the past and present combined. The future is dominated by configurations that we cannot directly observe. The future is predictable in principle from current physics, but inaccessible in practice to any plausible future observer. The cosmic story has a specific shape with a brief active middle and a long quiet aftermath, with the boundary between these two phases being marked by the death of the final star approximately 10 to the 17th years from the present. For the rest of the night, sit with the final star. It is out there, waiting to form. Not yet, of course, not for approximately 10 to the 17th years, but the physics that will eventually produce it is in the cosmos now, embedded in the various stellar populations and gas clouds and gravitational dynamics that will, across enormously long stretches of cosmic time, eventually conspire to produce one specific final stellar object. That object will burn for 10 trillion to 100 trillion years from its formation. It will die quietly, with no dramatic event marking the transition from active stellar burning to inactive cooling. And after it dies, no other star will ever ignite anywhere in the cosmos for the remainder of cosmic time. The 5 truths together describe a single specific object that does not yet exist but whose properties can be predicted from well-understood physics. The final star will be small at the absolute minimum mass for sustained hydrogen fusion. It will be dim, with luminosity at the lower limit of what any star can produce. It will burn for an enormously long time, far longer than any star currently observable in the modern cosmos. It will die in essentially perfect silence, without supernova or planetary nebula or any other dramatic event. And it will mark the absolute boundary of the cosmic stelliferous epoch, with the cosmic future after its death being enormously longer than the entire stelliferous era ever lasted. Picture, for a moment, the death of the final star as it might actually look. The star is a small, dim point of infrared light in some specific location within Milkomeda, the merged galaxy that will form from the eventual collision of the Milky Way and Andromeda. The star has been burning for trillions of years at the slow, steady rate that defines the late stages of low-mass stellar evolution. Its hydrogen supply has been gradually decreasing across this enormously long time. Its surface temperature has been gradually declining as the fusion rate slows. Its luminosity has been declining in parallel. In the final hundreds of millions of years of its life, the star transitions through the slow extinguishing of its nuclear fusion. The hydrogen abundance in the core becomes too low to sustain the steady main sequence burning. The fusion rate declines progressively until it eventually drops to negligible levels. The star contracts under its own gravity, with the gravitational potential energy keeping it warm for a while, even though active fusion is no longer occurring. The contraction eventually stops as electron degeneracy pressure becomes the dominant support mechanism, with the star having effectively become a small, dim white dwarf. There is no specific moment of stellar death. The transition is continuous. But there is a moment by any reasonable convention when we can say that the cosmic stelliferous epoch is over. After that moment, no active hydrogen fusion is producing fresh starlight anywhere in the cosmos. The cosmos enters the long, quiet aftermath that will dominate the remainder of cosmic time. Slowly, the camera in your imagination drifts outward. It leaves the room where you are sitting. It rises above the building, above the city, above the planet. It travels outward through the solar system, through the galaxy, through the local group. It pushes forward in time, accelerating through the cosmic stelliferous era. The bright young stars and active galaxies of the current cosmic moment fade. The middle-aged stars give way to older stars, then to red dwarfs, then to the rare merger-driven stars of the late degenerate era. The camera continues forward in time. It approaches the moment of the final star's death. Milkomeda appears in the field a diffuse cloud of stellar remnants floating in apparent emptiness. Somewhere within Milkomeda, the final star is in the late stages of its slow extinguishing, dimmer than essentially anything visible to standard astronomical observation, gradually approaching the moment when its fusion rate drops below any meaningful threshold. The camera observes this transition, recognizes it as the boundary of the cosmic stelliferous era, and continues forward in time. Past the death of the final star, the camera observes the long, quiet aftermath. The stellar remnants continue to cool. The brown dwarfs continue to drift through their gravitational orbits. The central, supermassive black hole of Milkomeda continues to grow through occasional accretion of stellar remnants. The cosmic time continues for enormously longer than the entire stelliferous era ever lasted. The camera moves through the degenerate era, the black hole era, the early dark era, with each phase being enormously longer than the previous phase. The camera turns around and begins the long drift back. Past the long quiet aftermath, past the death of the final star, past the late stelliferous era, past the middle stelliferous era. Backward through the long stretches of stellar activity. Backward through the cosmic dawn, backward through the cosmic microwave background, backward through the early universe, all the way back to the present cosmic moment, with its rich active stellar populations and its observable cosmic web and its empirical accessibility. The camera approaches the present cosmos from this temporal direction, past the galaxies of the cosmic web, past the local group, past the galaxy, past the solar system, past the planet, through the atmosphere, through the city, through the building, into the room, to the foot of the bed. You are still here. The version of you in this room, on this night, is alive during the brief active middle of the cosmic story. The final star is not yet born. The end of the stelliferous era is enormously far in the future. The cosmic configuration you currently observe is the active configuration that exists during this brief phase of cosmic history. The configuration is rich. The configuration is empirically accessible. The configuration is genuinely valuable, even if it is temporary in the cosmic context. What this means for how you experience the cosmos tonight is subtle. The cosmos around you currently contains active stars. The cosmos around you currently contains active galaxies. The cosmos around you currently contains the observable cosmic web. All of these features are products of the cosmic stelliferous era, which will eventually end with the death of the final star. The current cosmic configuration is, by every available indication, a transient feature of cosmic history. The cosmos will eventually transition into the long, quiet aftermath, with the stelliferous configuration being a brief earlier phase. The cosmic moment we currently inhabit is, in this sense, particularly valuable for empirical observation. The current cosmic configuration is rich. The current cosmic configuration is empirically accessible. The current cosmic configuration will not last forever, in the sense that the cosmic conditions that produce the current observational richness will eventually change. The empirical work we are currently doing has a particular cosmic value that future empirical work will not have, because future empirical work will be conducted in a much quieter cosmic environment. There is no need to hold all of this in your mind. The five truths will keep their shape whether you remember the details or not. The final star will form and die according to the well-understood physical processes, regardless of whether anyone is around to observe it. The cosmic stelliferous era will end at its expected time. The long, quiet aftermath will continue for enormously longer than the brief active middle. The cosmic story will continue with or without observers. The cosmos that contains your sleeping body is the active cosmos of the current cosmic moment. The cosmos is rich. The cosmos is accessible. The cosmos is empirically productive. The final star is not yet born. The end of the active era is enormously far in the future. The current moment is what you have. Sleep can come whenever it wants now. The story has done its work. The final star is out there in the cosmic future, waiting to form and burn and die at the appointed time. The cosmos now, in this room, on this planet, in this galaxy, is here, rich and active and accessible. Both cosmoses are real. Both are part of the same continuous cosmic story. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.